All right, we're going to go ahead and get started. The majority of this presentation will take place not in slides. I'll be doing a lot of stuff in like a image editing software, so I can essentially use it as a whiteboard. Because I feel like it's better that way for this kind of stuff. For the really physical concepts in chemistry, this kind of a really convenient way to learn stuff is visualizing. So first off, we follow 501 social media. It's the best way to get alerts about things. And we just had 2 more people join. Hey guys. So all this place or all these social media places, you can get notifications. I know I'm checking Instagram a lot. So it's a very good place to, get your notifications that you're already scrolling through it anyways. And I rarely check my email for this kind of stuff. Most people, I imagine, most teenagers aren't checking their email for this kind of stuff. So in general, it's just, good to have something that's constantly reminding you the resources Vital was offering is something common. So we're going to be going over bond length. It says review of potential energy, but I'll probably go a little more in depth with it since I imagine people in these slides didn't attend the first stream. I think it was the first stream. We're going to be going over stability and how potential energy relates to stability. Stability of just a general system. That could be a molecule, that could be a set of molecules together, that can be really anything, actually, anything you can define as a system. We're going to be talking about potential energy as a function of bond length. So each bond length has its own potential energy, and you could sort of see it as a function, kind of like a y equals f of x thing. Like if you have f of x equals like 5x squared, that's a really like tall parabola. That's the type of function. So the potential energy depends on the bond length. We're going to be talking about diatomics and their potential energy as a function of bond length. That's what the PBL means, potential energy as a function of bond length. And bond strength, which is essentially literally the strength of bonds between molecules. So first is bond length. We're going to be defining bond length right here. So bond length is just the physical distance between 2 atoms bonded to one another. So we have sodium chloride at the top. The bond length is the physical distance between sodium chloride. Same thing with atomic hydrogen, which is just diatomic in nature, or appears in nature as a diatomic. That also has its own bond length that's unique. There's water, which even though it has 2 bond lengths, the bond lengths are the same because bond lengths are unique between 2 elements. So, for example, here I love that I get to play with my model kit today. Here's water, right? Oxygen, hydrogen, hydrogen. And there's a physical separation between the oxygen and the hydrogen. And this is called the bond length. Same goes for a molecule like this. I think this is 1,2-ethene diol. And then for this molecule too, this has all sorts of different bond lengths. On the model kit, it shows the bond lengths all being the same just for convenience purposes, so they don't have to make a bonding toy for each thing. But the bond length is dependent on the 2 atoms and only the 2 atoms between them. There may be some variations just because of other interactions with the molecules around it, or other interactions with other atoms in the molecule. But generally speaking, they're pretty much identical amongst atoms, or amongst 2 atoms. So typical bond lengths are on the scale, or on the magnitude of 10 to the negative 10 meters. So that's really freaking small. Sodium chloride's bond length, or just the bond length between any sodium and chloride, is 0.24 nanometers, which is really small. Diatomic hydrogen, the bond between 2 hydrogen molecules. And in this case, you would say like this is between 2 hydrogen molecules, or 2 hydrogen atoms in any molecule. But you're never going to see hydrogen bonded to another hydrogen outside of the diatomic hydrogen molecule. That has a bond length of 0.074 nanometers. And water, there's 2 bond lengths, right? If you go to this slide from before, there's 2 bond lengths because there's 2 bonds, or 2 separate bonds. And that bond length is 0.096 nanometers. So these are really small, which means there's a strong force between them. whether that force be just purely electric, like in an ionic bond, or whether that force be caused by like a pseudo force of covalent electrons. So review of potential energy. This is going to be, I think, the majority of the slide is just explaining potential energy because it's really hard to get potential energy without a physics background. And I'm assuming most people that watch these things don't have a very strong physics background because you're high schoolers, and typically the high schools that do take AP Sciences anyway, a lot of them only take one AP Science. So I'm going to go bare bone like you have no physics background, which I think is appropriate. Potential energy exists as a result of an object having a force exerted on it, right? So, for example, you sitting in your chair right now, if you're laying in your bed on your phone or wherever you are, there's a force of gravity acting on you. As a result, you are an object that is having a force exerted on it. That force is gravity, so there's a potential energy in the interaction between you and the Earth. And in more of a chemistry concept, we'll look at this molecule right here again. There's a potential energy between all these molecules, right? Some of them are bonded, but in terms of the non-bonded ones, there's a very strong, or the most prominent potential energy interaction that affects the molecule is between these two hydrogens right here. These two hydrogens exert an electric force between each other, right? Or on each other, because opposites attract, likes repel, and these hydrogens are both positively charged. It's kind of the definition of hydrogen, or hydrogen without an electron, which is what these are because their electrons are being shared, and these are polar bonds, so it's being pulled away, all that good stuff. But essentially, this comes out to be a partially positive charged hydrogen. So there's a potential energy that exists between them because they're exerting a force on one another. They're going to be repelling each other like that, which causes this hydrogen to flip down like this, where these are the furthest apart from each other. And objects minimize their potential energy by turning it into kinetic energy. For example, if you're on your bed, you roll off your bed, you fall to the ground. Kinetic energy being the energy of motion. It's proportional to your speed squared. So the faster you're going, the more kinetic energy you have. And an object minimizes its potential energy to become the most stable. And as it loses its potential energy, that potential energy can't just disappear because energy can't be created nor destroyed. So that energy turns into kinetic energy, which causes you to move. That's the energy approach to motion. There's also the force approach to motion, but they're essentially saying the same thing, and you'll know that they're saying the same thing if you take a calculus-based physics class. So for example, if you have this molecule existing like this hydrogen, well, both of them actually, but we're just going to act like this one's rigid. It has to minimize its potential energy. And how it does that is by turning it into kinetic energy, by moving away. This is the only degree of freedom it can have. It can't just rip off the molecule. Well, it can, but this interaction is much stronger than this interaction, so it stays here. And what happens, it turns into kinetic energy by rotating, and then it exists in its most stable state when the potential energy is minimized. In terms of electric potential energy, which is what these two molecules are exerting or have in their interaction as electric potential energy, electric potential energy is a constant times the product of their charges divided by the distance between them. So these both have positive charges, right? So plus one, the product of that is plus one. So essentially the potential energy becomes a constant over the distance. And how it minimizes its potential energy is by increasing the distance, right? Because if you have a number over a variable and that variable at the denominator increases, that original number goes closer and closer to zero. So the lowest this interaction can have is zero. So, but that's only at an infinite distance. And the maximum distance it can have is between here because this interaction is keeping this hydrogen on this oxygen. So that's pretty much a crash course in potential energy. It's a really hard concept to understand, especially when you start going into things that are more abstract, like, for example, nuclear potential energy or even chemical potential energy is hard for some people to understand because we don't see chemicals doing this with our, naked eye, because that's just not how the world works. These are really small, too small for us to detect with our eyes. And how stability relates to it is an object is in its most stable state whenever its potential energy is at a minimum. Yeah, so a redox reaction every reaction has some associated change in potential energy with it. But that potential energy is more of a macroscopic thing. For example, like if you have two waters right here, like this negatively charged part of the water will attract this positively charged water or part of the water, and there's going to be a force between them, but it's not necessarily like a bond energy. It's an electric energy. And essentially the potential energy would be all of the like water molecules in the solution, the interactions and the energies added up together like a sum. So every reaction does have a potential energy that's mostly electric, but they're not intertwined. Electrical potential energy and redox, like it's a much different concept. Like redox reaction is just essentially the exchange of charges, but charges moving isn't what causes the potential energy. Charges being static and having a distance between each other is what causes electric potential energy to exist in an interaction. So in short, yeah, but not for any special reason. All reactions are related to electric potential energy. In the case of redox, it's just charges moving around, but how charges move around isn't, on a macroscopic scale, doesn't really change the potential energy. Does that make sense? Okay, so back to stability. An object is in its most stable state whenever its potential energy is at an absolute minimum. So in this case, we're looking at a graph that says potential energy is proportional to x squared. And for what value of x do you guys think the object is in its most stable state? X could be anything. Probably best analog would be distance here. Yeah, whenever the object is in its most stable state, what it'll tend to. Give you about 10 more seconds. Yeah, the lowest point of the graph. So that's at x equals 0. And that should be a pretty simple concept. We're going to go a little more in depth with why. Because you guys probably understand the concept of a force better than an energy or an energy in like a force interaction. Like I'm exerting a force on my hand right now with my other hand. You know, it's a pretty it's all around us. We simply live with it. So we'll go from that analog because we kind of have to fully understand potential energy diagrams, which we'll talk about. So yeah. So the next thing, before I move on, anyone have any questions about that set of things with bond length and potential energy and stability? Any questions at all? Don't be scared. No dumb questions. As in, there are no dumb questions. Not that I don't want you to ask a dumb question. All right. So the next thing we're going to be looking at is how potential energy relates to bond length. A little bit of a trigger warning. You're going to see some math on the next slide. The purpose of the math isn't to give you, or you're not supposed to memorize the equation. It's just a form of conceptualizing it if you want to graph the equation and see for yourself. But here we go. So potential energy between two bonded atoms exists as a function of bond length. So like I said before, like f of x equals 2x plus 1, the potential energy exists as a function proportional to that thing. Sigma is just some random constant, or it's not random, but it's a specific constant specific to each bond. It just makes the quantity sigma over r. Sigma is that funny looking Greek letter with the almost looks like a little boy wearing a hat. It makes that quantity dimensionless, so you can subtract the two quantities like you should normally be able to. And in this case, force, like the force that exists between the two atoms, is the negative slope of this graph. And that's just by Newton's laws. I imagine you guys know that, like, when the net force on an object is 0, when all the forces balance each other out, the object doesn't move, right? So, for example, if we have like water right here, there's an attractive and a repulsive force as this bond force. So at some point, that force has to equal 0, right? Or else this would keep on moving around and the atom would collapse or the molecule would collapse and all that good stuff. So there has to be a point somewhere where those forces bounce each other out. The force is 0. The hydrogen bonded to this oxygen doesn't move, and then you have a stable atom. So no, definitely don't memorize that. The whole point there is to get you a conceptualization of it, because I remember when we were taking practice tests last year in my AP Chem class. I'm a physics major in college right now, so I'm a physics guy. So I have to know this stuff like the back of my hand, right? And we had a question that I had never seen before in a chem class. That was exactly like this. It was, at which point on the graph will the atom lie? It was this exact graph, potential energy versus position. And no one knew how to answer the question because nobody knew how potential energy related to force and how force related to motion. So I'm going to challenge you guys real quick. Do you guys think the force is repulsive or attractive above the horizontal axis? And remember, it's the force is equal to the negative slope of this graph, or the force at any x is equal to the slope of the graph at point x. So the force above the horizontal line is either repulsive or attractive, and I want you guys to, at the very least, throw a guess on which one it is. Repulsive, obviously, meaning the atoms are repelling each other. Attractive, meaning they're attracting each other. Yeah, that's right. Yeah, it's repulsive. And the reason why is because the slope above the horizontal axis is negative, right? I hope everyone can see that the slope above it is negative no matter like what x point you are, as long as it's above the horizontal axis. So if the slope is negative, the negative of a negative number is a positive number. The force is positive, which means the force is repulsive, because the force is what creates an acceleration. So if the force is positive, that means the atoms are accelerating away from each other. Does that make sense? This kind of thing, like it's good to like have this stuff in the back of your head. However, if you're having trouble with this kind of concept, don't worry about it. Like don't stress over it. There are really rules you can memorize about these kind of graphs. And if you're much better at memorizing the rules, I philosophically disagree with that because I'm a physics major, so I'm biased. But you'll be fine. You can just memorize the rules. This is going to be at most a multiple choice question or two on the exam. And the way the exam is graded, you get a 75% or better, you'll typically get a 5. So you can miss 1 or 2 multiple choice questions if you miss a concept. So I'm going to ask another challenge question. What do you guys think the blue line represents on the graph? Doesn't the point/molecule move on the graph? No, the graph isn't like a physical thing. It's not like a physical like path that it takes. If you want the most technical answer, there's a range around that blue line where the molecule oscillates like a spring, like a block on a spring that's like oscillating up and down. There's a range where the molecule oscillate, but that's just between like one x point or one distance between another distance, so it just moves back and forth in like a linear line. And obviously this is like a big simplification, right? Because molecules don't exist in one dimension; they exist in 3 dimensions. So you need a 3-dimensional graph to do this kind of stuff completely accurately, and that would be potential energy as a function of 3 variables, which would lead to a 4-dimensional graph. And if you can imagine a 4-dimensional graph in your head of this, you need to quit watching the stream and apply to like MIT because you have spatial abilities that I've never seen out of any other human being. because we kind of got sidetracked, the blue line just represents the most stable position or the most stable distance between the two in this interaction, just because that's where the potential energy is at a minimum. So that's when it's most stable. Oftentimes you will be asked, like, at what point is a molecule most stable? And that's just the minimum potential energy. You won't, I don't think you'll be asked whether the force is repulsive or attractive to the left side of the blue line or the right side of the blue line. But if you are, hopefully you remember this. If not, no big deal. It's just one multiple choice question. So to the drawing board. So we're going to look at this graph a little further. I'm about to pull up a graph that has, actually, hold on. I can pull up the graph that only has one just to make it a little less cluttered. Okay, so I'm going to switch screens. Sorry, I'm a little big right now. Application window. There we go. Let me move this more. So when we're talking about like the slope of a graph at a point, I'll make this orange, or I'll make it green actually. Green's probably going to be the most visible color. I'm just going to make a random line and then match it with somewhere on the graph. So when we talk about the slope of a graph at a point, what we're really talking about is where the slope or where the line kind of brushes on the curve. That's really as like technical as I can get with it, unless you know calculus. But for example, like this is literally just a line slightly brushing on a curve, like a linear line, slightly brushing on that curvy line. And you can calculate the slope of that line right there that barely touches the curve at some point. For example, this touches the horizontal axis at some point right here, or this touches the curve at some point right there, which means that you can calculate the force at that point that I just brought up to the horizontal axis with the orange paintbrush by just calculating the slope of that tangent line. So there's something really cool about the lowest stability point. What's the slope at the most stable point, guys? The slope of the graph at the most stable point. What do you guys think? Yeah, it's 0. So we know, or now you're about to know, that force causes an acceleration. A force on an object causes an acceleration. So whenever an object is at a standstill, it's got to have 0 acceleration, which means there's got to be no net force acting on it. So at the most stable place, when the potential energy is at a minimum, also corresponds to the point where the force on the object is 0, which physically means all the forces on whatever object you're talking about are equal and opposite to each other, so they cancel each other out. Like if you're sitting and your feet are on the ground right now, there's a force of gravity that are pulling your feet down, but there's also the force, the earth exerts a force back on your foot, and those forces are equal to each other, which is why your foot doesn't move. So you can have a bunch of, you can have like a graph that looks, for example, like, I need to make that a paintbrush. You can have a graph that looks something like that. And as you can see, there are multiple places where, where the force is 0. There are multiple places where the slope of that tangent line is 0. But it'll always gravitate towards its most stable state. And its most stable state is whenever the potential energy is at a minimum. Now, if you have something like a downwards facing parabola, you have a problem, right? Because here the potential energy is at a maximum. So you'd expect it to be very unstable. But at the same time, the force is 0 because the slope of the tangent line at the top of the curve is 0. So there's a discrepancy here. And when we're talking about this, for example, we'll take this empty water bottle that I should definitely be throwing out sometime soon. If I balance it on my hand like this, or if I balance it on my hand on the cap, which one do you think is the most stable state? When it's balancing on the bottom of it or on the cap? Right. And the reason why is because the potential energy is higher as it moves like that because of the force or because of the interaction it has in my hand. Yeah, because of the interaction the bottle has in my hand, the potential energy will be higher. However, when it's like this, the potential energy will be lower. The potential energy will be lower like this. So if you could balance this bottle perfectly on the tip of it, it would stay standing up until someone else acted on it. But for example, if you have like a pencil, good luck balancing this on the tip of it. But if you could balance it perfectly on the tip of the lead, it would move. But it's highly, highly unstable because it much more favors to be in a different position. And then once it falls all the way, it turns its potential energy into kinetic energy by falling. Once it turns all the way and lands flat on the table, its potential energy is zero again at a minimum, which also implies the force is zero. Potential energy is lower, so it's able to move less. Yeah, essentially. Potential energy determines how much something can move, because in order for something to move, it would have to gain kinetic energy somehow, and that kinetic energy is gained from the object's potential energy, which turns into kinetic energy. Does that make sense, guys? Yeah. So this kind of graph can exist, but this state right here is highly unstable for the reason below, or the reason I just described. If it stays perfectly at this position, I need to get way better drawing this stuff. Geez. It can stay at this position if nothing acts on it, but as soon as something acts on it, it just shoots down. And again, you can see that if you try to balance a pencil perfectly on its tip. So in the same case with the molecule, this is just a potential energy diagram, and it'll exist at position X. Now, more properly, it'll oscillate between two positions. Some position like right here, and some position like right here. It'll oscillate back and forth. Oscillate mean like, an oscillating fan would go like that. Oscillating just meaning something like literally moving back and forth, like a pendulum, for example. If I do this, the pencil is moving back. The only reason it's not fully oscillating is because there's friction between here, so it's losing energy that way. So yeah, that's pretty much all that. A little crash course in physics. Hope you guys didn't hate that too much. I'm a firm believer that, like, if you know the physics of it, these kind of concepts become a lot easier to understand, especially when you apply them in a chemistry context, because a chemistry context is like it's very difficult to fully understand, because like on a chemistry concept essentially physics, but like a lot. Like a physics problem would be like a ball dropping, but like a chemistry problem would be like 10 to the 23rd individual molecules moving around. So once you know once you know at least on a base level how stuff is happening, then it's a lot easier to apply it. So chemistry application now, diatomics. So does anyone know what a diatomic is? Okay, so a diatomic, some molecules exist in the air as single molecules, like argon, for example, will exist as just solely argon. However, hydrogen gas, nitrogen gas, oxygen gas, chlorine gas, all of those, there is a mnemonic you can memorize to know if something will exist as diatomic or not. They'll exist as two things bonded to each other. So, for example, I have another way to represent this in a modeling kit. Some molecules will exist like this as a single atom in the air or in a liquid. But diatomics exist like this, like two of the same atoms bonded together to make a molecule. It is worth memorizing the diatomics. I don't have that on the slide here because it's really not too important for AP to like rote memorize them. But you can look up, honestly. There's a mnemonic called halogen Han, which means all the halogens, and hydrogen, oxygen, nitrogen. Those will all exist as diatomics in their gaseous form. So, a challenge for you guys. Which curve represents the potential energy curve for hydrogen gas? Which one do you guys think? Which one? Just name the color. There's red, blue, and green. And the three curves are chlorine gas, oxygen gas, and hydrogen gas. And this potential energy curve is between the actual bonds between the individual molecules, like we were talking about before. No, green is chlorine gas. And it's also wrong. that green curve should never cross the vertical axis again. That's my bad. But the answer is red. And the reason why is because if you look at where what position, at what bond length the molecule is the most stable, hydrogen has the lowest one. And that's purely because hydrogen is a really small atom, right? Like chlorine has a nucleus, oxygen also has a pretty large nucleus, or has a lot of electrons rather. The electrons make it bigger because of electron shielding. Blue is oxygen gas. Yeah. And we'll go into each different shape of it, right? There's two distinct, or there's one distinct characteristic of the red one, of the hydrogen one, and that's that it has the lowest, most stable bond length. There's one characteristic of the blue one, which is that it has the lowest minimum potential energy. And there's one characteristic of the green one, which is that it has the highest bond length. We're going to be talking about that a little bit. Do you guys know Lewis structures? Or Lewis dot structures? Or Lewis diagrams? Yeah. So let's go to the drawing board again. Application window, share. Okay, so we know that this one is hydrogen gas, which is diatomic. It's ugly too, whatever. This one is oxygen gas, not chlorine gas. And this one is Cl2. So when we're talking about hydrogen gas, hydrogens are like a really small atom, right? I hope you guys know that. If not, we can talk about that briefly. Do we need to talk about that? Yeah, anyone else need a briefing on that? So I'm totally willing to give it. Okay, awesome. So this bond length is pretty much like based on the actual size of the atom. And the reason why is because these are all covalent bonds, right? So if we have a hydrogen molecule, we'll label the nucleus, or we'll draw the nucleus blue. We'll have another nucleus over here. And then there's an electron between them that they're sharing. There's actually two electrons that they're sharing. How fancy. And then there's orbitals around each of them. So hopefully you can see from this diagram that the specific diatomic, this is like almost solely based on the atomic radius here between the two hydrogens. And the same case goes for oxygen and chlorine. And chlorine's bigger because chlorine has more electrons. So that bond length is even bigger. I'm going to label the bond length just to be a little more rigorous about it. This is the bond length. And from here, you can estimate that like the bond length is about twice the size of the atomic radius. That's not exact, but it's important to know that that bond length for a diatomic is definitely some number that's about 2 times that atomic radius of that molecule. So in this case, this hydrogen has a bond length of about that X value. I can draw straight lines. I need to work on that. It has a bond length of that X value. Oxygen has a bond length of that X value. Gas is oxygen. And then chlorine has that value. And now to go over some of the actual like minimum potential energy values. So you guys see here that oxygen has the lowest potential energy in its minimum or its most stable state. And does it make sense to you that like, or to you guys, that it has the lowest potential energy state, so it's the strongest bond? Does that concept make sense? Okay, so Matthew, the stability relies on the potential energy being a small number or a very low number, right? So oxygen in this case has the lowest potential energy, so it is the most stable out of the three. So because it's the most stable, it has the strongest bond. It's hardest to pull apart. Yeah. So when we're drawing the Lewis structure for hydrogen, this is just simply that, right? Does that make sense? I'm going to leave out the electrons just because they're not really important in this case. But that's the Lewis structure for hydrogen. Now when we look at oxygen, however, oxygen has a double bond. So double bonds are a lot stronger than single bonds, and triple bonds are a lot stronger than double bonds. Can anyone provide an explanation for why the chlorine potential energy or minimum potential energy is higher than the hydrogen potential energy? Just any guess at all? Oh yeah, the answer is almost always electrons. The reason why, yeah, atomic radius. That's more right. Chlorine has a larger atomic radius, so the interaction between the two molecules is weaker, just because the interaction strength is inversely proportional to the distance. Does that make sense? Increasing the distance would decrease the strength of the interaction. Okay, cool. So that's how you solve these kind of problems. Often I go the stability route because if I vaguely remember there being some exceptions to the size rule. So the stability route is always the best way to go. Draw out your Lewis diagrams and see which molecule has the strongest bonds. And obviously a triple bond, or not obviously, as I mentioned before, the triple bond is stronger than the double bond, is stronger than the single bond. If you have two single bonds, or single bond versus a single bond, you can look at the size of the atom, and that will determine which one is stronger, because the larger atoms will have a weaker interaction. So that's that. Any questions at all? Awesome. So we'll keep on going. Bond strength. We were just talking about this. Bond strength is a measure of how much energy is required to break a bond. And there are two types of bonds. A chemical bond is more like what we're talking about, but there's intermolecular versus intramolecular. And intramolecular bond strength is much stronger than intermolecular attraction strength. So this is 1,2-cyclobutane-diol. Or no, cyclobutane 1,2-diol. And there's a lot of potential energy interactions here because this is just a big atom. So these black are all carbons, these whites are hydrogens, and these two reds are oxygens. So when we're talking about the molecule, the molecules can rotate around these single bonds. You don't have to know that, but like as they rotate, the potential energy between the two hydrogens changes, which is a cause potential energy. So the most stable would look like this, right? However, the intermolecular versus intramolecular. Intramolecular is an actual chemical bond. So if we have a water here, this interaction, is this intramolecular or intermolecular? You guys you can go ahead and answer that. The bond between this hydrogen and this oxygen, is it intermolecular or intramolecular? No, it's intramolecular, but I haven't given you an example of intermolecular. Intermolecular would be like a big vat of water. There's interaction between this negative one and this positive one. It'll go like this. They'll attract each other, right? Because opposites attract, but they're not bonding to form a chemical. They're bonding it's a intermolecular, intermolecular, inter meaning between, and intra meaning inside. So they're between molecules, but the intramolecular is inside the molecule. And covalent network solids, for example, graphene. So this is just a bunch of carbons bonded to each other. And if you've ever seen graphene, it's pretty big, but it's not intermolecular bonds that make it big. It's intramolecular. It's a bunch of carbons that are bonded to each other. So this is solely intramolecular forces, even though it's really big. When it's really big, it's actually one big molecule for things like graphene and diamond. That's why diamond is so tough. For example, a big sheet of graphene versus, we're going to compare these things. A big sheet of graphene is just a bunch of carbons chemically bonded to each other, but a big vat of water or solid water is a bunch of individual molecules that are attracted to each other via a polar attraction like this. Does that make sense? It'll probably, if it doesn't make sense, it'll make more sense when I show you the infinite structure of graphene, because this is obviously just a segment. So the challenge is, which solid substance has a higher melting point, ice or graphene? Throw a guess out there. Yeah, it's graphene. Graphene has a boiling point. I'm going to go with water first. Water has a boiling point of 373.2 Kelvin. Graphene has a boiling point of 4,510 Kelvin. That's 78% the temperature of the sun's surface. And the reason why is because intermolecular forces are way stronger than intermolecular forces. And the thing that's holding the water together into a solid is an intermolecular force. And the thing that's holding the graphene into a solid is an intramolecular force, which is the covalent bonds between the carbons. Here's a full sheet of graphene. This goes on infinitely, theoretically. I obviously could only show you 2 little hexagons because I'm not made of money, so I could only buy 1 model kit. Whoopsie. So that's a full sheet of graphene. I'd recommend looking at the structure of diamond to see how it looks. It's really cool, and it makes a lot of sense that graphene is a very tough molecule. I was going to correct myself and say a tough object, but it's actually a single molecule too. It makes sense that it's tough when you look at it. It's all intramolecular bonds. There's no intermolecular forces like you see with like a piece of ice, or like even this like paper right here that I should also throw away. I need to stop being sloppy and messy. The paper's held together by intermolecular forces, just because those molecules don't chemically bond to one another. So some examples, these are very important to know, are diamond and silicon dioxide. Silicon dioxide is just glass. And if you don't know, glass is also sand. Those are the same thing. That was also kind of a mind blow for me. Silicon dioxide, it does form to create this big single solid of chemical bonds. Same with diamond. Those are important to know. It's important to know the properties, that they have a very, very, very high boiling point because they are covalent network solids. I think one of my other team members is streaming different types of solids, and I haven't seen the slides, but I'm sure they mention covalent network solids. So single, double, and triple bonds. Some atoms have double bonds, like nitrogen. Some atoms have single bonds, like methane. Or is that ethene? That's either methane or ethene. I need to study for OChem. In general, triple bond is greater than a double bond, and a double bond is greater than a single bond in terms of strength. And if number of bond lengths are the same, you estimate the bond length using periodic trends, and that specific periodic trend that you estimate with, it might be ethyl. If it is, then I'm being an idiot, and I wouldn't put it past me because I did really bad on my first OChem exam. So now OChem scares me. But if the number of bonds are the same, you estimate it with atomic radius. So we're going to do another practice problem. Which process do you guys think requires more energy to complete, A or B? A is just nitrogen gas splitting into 2 individual nitrogens, so the actual bond breaking between the nitrogen, and B is the same thing with the oxygen. Yeah, it's nitrogen. The answer is A. And the process is you draw the Lewis structures for both N2 and O2. you'll see that N2 has a triple bond while O2 only has a double bond. Thus, the NN bond is stronger than the OO bond. More accurately, that NN should be a triple line, not a single line. And the OO line should be a double line, not a single line. That doesn't necessarily represent the bond itself. That's just a grammatical hyphen thing. So to the drawing board, we're going to be drawing these out. So I'll make a new image here. So does anyone know off the top of their head how many electrons nitrogen has? It's 10, right? Yeah, it's 10. So drawing out the Lewis structure, there obviously has to be a bond between the nitrogen. And there's going to be 10 valence electrons because nitrogen has 5 valence electrons. You can see that on your periodic table. So you have to fill up some spaces here. And the only way to fill up that space is by creating a triple bond in the nitrogen and giving lone pairs to each nitrogen. You can count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 electrons. So nitrogen has a triple bond. What do you mean has 7 on the periodic table? What do you mean? 7 atomic number, that's just a definition of hydrogen or nitrogen. But the group it's in is what determines how many electrons it has. You'll see that it's in group 15, I think, which means that it has 5 electrons. If you're having trouble with that, there's stuff on Khan Academy about that. And Khan Academy is also a great resource in general. So oxygen, individual oxygen has 6 valence electrons from the periodic table again. So we draw 2 oxygens. There has to be at least one bond between them. So now we have 10 electrons, and you'll find the way to do that is double bond with 2 lone pairs on each one. Let's count those. Do it in blue this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just drawing out the Lewis structures, nitrogen, very clearly, there should be lone pairs on that nitrogen, just in case people are taking pictures or watching the recording of this later. Nitrogen has a triple bond. That triple bond is stronger. It's a stronger interaction. That should make intuitive sense that the triple bond is much stronger than the double bond in terms of bond strength. If it doesn't, just let me know in the chat right now, and I could sort of talk about it. It'd be pretty hand-wavy because I don't know how to formally explain that kind of thing. But you can go ahead and ask. All right, I'm going to guess that means no questions with that. So back to the slides. This stream took much longer than I thought it would, so we're not going to do any more practice, but we're not going to do more practice problems. We will have an open discussion, however. So does anyone have any questions about this kind of topic at all? Because I have 10 more minutes until I have to do something. So strength is more reliant on so when we're looking at 2 single bonded atoms, the bond length is what matters. I wouldn't, because it depends on how you're measuring strength. But the bond length, the strength will be stronger if the bond length was shorter. So no, it's not directly related. It's inversely related, inversely proportional. Yeah, sure thing. We'll go back to the slides. Actually, no, we don't need the slides to talk about this. So intermolecular, let's look at the water molecule again. So there's some forces going on at play right here when we have 2 things together. So do you agree that it makes sense that there is some force amongst water molecules, or else there wouldn't be liquid water? It would just be individual atoms like a gas, right? Do you agree does that make intuitive sense that there has to be some force? All right, so when we have 2 molecules, there's some forces going on in play. Intra means in, and this means in the molecule. There's forces inside the molecule holding it together. There's a force between this hydrogen and this oxygen. Inter means between. So between the molecules, there's a force here, right? So if we have two water molecules right here that are directly like this, they're going to repel each other. That should make sense because there's a positive, a positive, a positive, a positive, and these are dominant because they're close to each other, so they move apart. However, what actually happens is one of these rotate because oftentimes they're not completely still like this. So one part is dominant over the other. So they rotate like this, which creates like something like this. And there's an intermolecular force. There's a force between the molecules because this is positively charged and this is negatively charged, and opposites attract. So they move like this. So that's an intermolecular force. And you'll learn more about intermolecular force and what the different types are, how to determine the strength of an intermolecular force. But this is pretty much this is what it is, the force between molecules, where intra is the force inside molecules. Does that make sense? Did I answer the question? Awesome. Okay. Anything else, guys? All right. Awesome. If you have a question, I'm putting my Instagram in the chat. You can feel free to DM me a question. If it's a homework problem that you want me to talk you through, I can give you my Discord through my Instagram, and we could just, actually talk about it through microphones and voice, or I could draw it out, share my screen, all that good stuff. But yeah, I think we're good here. You guys agree? Awesome. So that's it for the stream. Again, follow Fiveable on social media. I will be streaming next week again. I don't remember what my topic is, but I should probably know that. So yeah, that's it, guys. Hope you guys have a good night. Take it easy.